Hello everyone and welcome to another Leetcode solution video. In this video, we'll go through converting sorted array to binary search tree. In this problem, we have an integer array and this array is sorted and in ascending order. We want to convert it to a high balanced binary search tree, as you see in those two pictures. Both solutions, both outputs should be fine if you have the following array. What is the high balance binary search tree? It is a binary tree in which the height of the left and the right subtree of any node differ by not more than 1. What does it mean? We have a tree. This is our root and this is our left subtree. This is our right subtree. If you count the height of each subtree, the difference should not be more than 1. There are conditions of the height balanced binary tree, and these are 3 conditions. The difference between the heights of the left and the right subtree for any node is not more than 1. The left subtree is balanced and the right subtree is balanced. These 2 conditions already say that we should use the recursive function. It's a recursive procedure. Height balance of node equals to height of right subtree minus height of left subtree. Let's count the left and right subtree. 1, 2, 2 nodes of the left subtree, and 1, 2, 3, 1, 2, 3. Basically, the largest is the 3 nodes of the right subtree. On the left side, this is a height balanced binary tree. On the right side, you have the opposite. It's not height balanced binary tree. Why? Because if we count the left side with the length of the right side, the difference is much more than 1. 1, 2 versus 1, 2, 3, 4. 4 minus 2 is 2. That's why it's not a height balanced binary tree. Now let's move to the drawing of the solution. In this array, each value has its own index. For example, we start from 0, 1, 2, 3, and 4. If you noticed, our root has the value of 0, which is in the middle. That means that our root is always the value from the middle. How do we find out which index is the middle? Index 0 is always our left pointer, and the last index is always our right pointer. If we left index add to the right index and divide it by 2, we will have the middle. Zero plus 4 is 4. 4 divided by 2 is 2. The value 0 is under the index 2. Before we find the middle index, we should always check if the left index is bigger than the right index. The left part of the array is our left subtree. The right part of the array is our right subtree. If our left index is bigger than the right index, it means we return none. It means that there is no node. Like here, for example, no node. Or here there is no node, here there is no node, here and here, no. Here and here. All these blue dots are non-values. What we should do next is to recursively iterate through each subtree. Let's first go through the left side. On the left side, left index stays the same, 0. Right index will be 1. If we add 0 plus 1 and divide it by 2, we will have 0, which means that the value under index 0 is our new root, is the root of our left subtree, -10. According to the recursive iteration, middle index -1 will be our new right pointer. There is no value under -1 index. 0 is bigger than -1, and we return the value none. Now we iterate the right side of the left subtree where the root is -10. In this case, -3 becomes the right pointer, the left pointer, and the middle, because 1 plus 1 divided by 2 is 1. 1 plus 1 is 2, divided by 2 is 1. That's why it also becomes the middle, and it becomes the new root, but on the right side. Coming back to the right subtree, we have 5 and 9. Moving to the right, we have to add to the middle index plus 1. Middle index is 2. 2 plus 1 is 3. So here will be our new left pointer. 3 plus 4 will be 7, divided by 2 is 3. This means that it's our new root in the right subtree, as you can see here. Now we move right again. If this was our middle, we add 1, and again 9 becomes our right pointer, left pointer, and the middle. 4 plus 4 is 8. 8 divided by 2 is 4. We append this node to the right side. Now let's do the same in Python. As we said, we have to use the recursive function. We will use this function with two parameters, left and right, in order to know what is our left pointer, the index 0, for example, and the right pointer, the last index in the array. As we said, we always have to check the condition if the left node is bigger than the right one. If it is, then we return none. We want to choose the middle element as the root. First, we have to find out what is the middle element by adding left and right and dividing it by 2. Then we create a tree node with a value that is at the index of the middle node. This we place into the root variable. Now we want to recursively construct the left and right subtrees. We start with the left one. We take the root because this is our starting point. And we first go to the left side, building the left subtree. We run the same function with different parameters. Left stays the same as 0, and mid minus 1 because we move to the left side of the array. The same we do with the right side. But in this case, we have mid plus 1 because we move to the right side of the array. In this function, we return root, but the function sorted array to BST will have to return the recursive function with 0 because the array starts always at index 0, and we calculate the length of the array, and we subtract 1 because since we start from 0, the length should be always subtracted by 1. Let's check if it works. We have 0, minus 10, 5, none, minus 3, none, 9. Let's compare. Zero, minus 10, 5, null, minus 3, none, 9.